people interested. So you can define a map which is defined on the circle, which essentially, because we have a closed loop, which goes from the circle into the circle. And there's something in mathematics and topology which is called the degree of a map between two circles, which essentially records how often you run around one circle runs around a second circle. And we have this curve, which by normalization also takes 1 and S1, and the winding number of this is equals to the degree of this map. So if you don't know what the degree is, just ignore that side remark. Otherwise, that's something maybe interesting for you to think about. Would like to record some properties. So the first part is that the winding number depends on the point. That we have seen in the examples. Like I can take the same curve, but the winding number depends really on the point that I choose. There's something of where it's actually independent, and that one is that if you have if you can vary like the point slightly. So if you choose some other point, then the winding number around this point and this point will be the same. Same thing at the points between here. And also similar, I can choose like a different point. But the important part is I can only vary the points as long as I don't pass past like the curve limit. So if there is a connection between these points and this connection does not intersect with the curve again. And it's maybe not like too important because I run kind of out of time, but like the important part is that there's like a formula of that form is where we calculate the number of this number how often the curve winds around as an integral over time of something, and that something is related to the curvature, but it's not so important. Like yeah, if you're interested in that, you can look that up in books. But it's kind of cool to know that that you can represent like something that is discrete and that counts how often you turn around as like an integral over time over a certain integrand that's relatively complicated. But I just wanted to show you that there's a formula like that, if you're interested. But what I would like to discuss instead is namely something that is way more interesting, and that's like curves in 3 dimensions. So far we only concentrated on curves in 2 dimensions. We were always thinking about curves that I could draw in a blackboard, essentially. So something that lives, like a curve that lives essentially on the blackboard. But like usually in life, curves live in 3 dimensions, right? So that, like this curve. And you can also ask like the same thing with closed curves. And what you have already seen that some of the properties that we discussed. Okay. So we have already seen that some of the properties that we discussed for curves in 2 dimensions don't hold any longer for 3-dimensional curves, right? Like, I gave you this example of like the inside and the outside of a curve. It's no longer clear what is inside of a curve in 3 dimensions. Yeah, so there will be a certain elements in 3 dimensions which will be different. But one of the things that can be translated relatively straightforward is this concept of the Frenet or Frenet-Serre frame. So that is what I want to discuss now. And discuss how that is like connected to curvature again. Okay, and the first observation is that there's two kind of things that can happen for curves in 3 dimensions. First, we can as well kind of bend, right? So what I'm with bending, I mean something like this. It's like a curve that has like some bending, like it's like bending would be then again something where it deviates from being like tangent, where it's not like a straight line. So that's it's kind of like the bending, and we have already seen that this is kind of something that is measured by the curvature. And essentially, if you can think of like a curve, like locally, what happens is that, like in a small neighborhood, I can always approximate like a curve by a plane that looks like something tangent and something normal. So locally, there's not much difference between what we discussed so far of like planar curves and something that happens in 3 dimensions. So local, you can say like we approximate like whatever curve we have by some kind of sheet of paper, and then measure the bending of the curvature as something that relates like in this plane, like this same as the curvature of a planar curve. But what happens if you have like a curve that is kind of like something like holding like that, is that if you approximate this now with like a plane, then you go along the curve, then this plane will move, right? Like this plane of like the curve where we approximate the bending in, like will change if I go along the curve. That's a bit hard to demonstrate, but it's like these two different effects that like we have like something two-dimensional, which is again the curvature, and then this two-dimensional plane will shift along the curve. And that's something that is called like the twisting. So the bending is again kind of like how much the curve deviates from being a straight line. In a plane. And then there's this that is approximating plane can like also move, and that's what is called twisting. And that's as we will define now. It's measured by what is called the torsion of the curve. And as I kind of try to illustrate it by the sheet of paper moving along the curve, that measures how much this plane rotates. We have an approximation in a certain plane that I will define also in a second, and the twisting will describe how much this plane changes and twists. So that's kind of like to give you a rough idea. But of course we need something more, right? Like we need like some kind of formulas. What is actually like twisting and bending, right? Like otherwise, like I can't give you homeworks to calculate same things. So let's write down formulas. The first thing is that we need like a unit speed curve. In 3 dimensions this time. And unit speed, again, is like, we just like assume for simplicity. Then the first vector that we define is just the first time derivative of the curve. And that's what is called the tangent. Tangent field sometimes. And then we have already seen, like the next step would be the second derivative, and the curvature measures second derivative, so the absolute amount. So this one gives you a vector in R3, and then we just take like the normal inner product of that vector with itself and take the square root of it. And that's by definition, we define that one to be the curvature again. That comes from the same argument as in the 2-dimensional case, and like what I tried to argue before is that locally we can always assume that our curve is kind of in 2 dimensions, so the argument with the oscillating circle and stuff kind of gives a justification why you would call that the curvature of the curve. And now we assume, what we already assumed quite often, is that the curvature at a certain point is like bigger than 0. And we do that because we want to normalize our second derivative. And we have already seen this one, our normal field. So far there's nothing really new. That's like mostly translating things from 2 dimensions and 3 dimensions. The important difference here is that these are now vectors really in 3 dimensions and not in 2 dimensions. So maybe I'll write this down. This one is really a vector in 3 dimensions, and so it's the normal vector field. So every time you get like and then once we have 2 vectors, we know how to construct a third one, right? Like you have like seen the hand rule like multiple times, I think, by now. So you just like say like this one is showing it like in tangent direction. So you go, if you have your curve, kind of twists. So you go like in tangent direction, you go with like the first finger, then you choose like the normal direction, and then binormal, like the vector that I'm going to define, it's like this third vector. So and then you go along the curve like this to get like a field of vectors at every point. And this vector that we can generate by this one is usually called B of t. And it's the exterior product. And it's called by normal field. So we have 3 vectors that shouldn't come as like a big as a surprise. And the point here is that these 3 vectors called linear direct frame. So that's a frame that is really defined in terms of the curve in itself, because the ingredients for the first 2 vectors were like the first and second derivative of the curve, and then this binormal is just like by the right-hand frame. So that's really like a frame that is adapted to the curve. So the first remark is that all these 3 vectors observation is that they are orthogonal to each other. I think that's like straightforward if you know like the right hand rule. That's like exactly like just you can see that either by calculating, but it's like clear for the same reason as we had before that t and n are orthogonal to each other because it's like take the derivative of the constraint that t is like a unit speed curve. And then this one is like orthogonal to both of these vectors by the construction of the cross product. So that's clear. And so the only somewhat tricky question is to ask yourself, like, why do they have unit length? And t has unit length because by assumption we have a unit speed curve. N has unit speed because we normalized it. So that's also clear. So the only question is why b of t has unit length. And there we use like a formula in order to calculate the length of the cross product. I think you've seen the formula enough. This term vanishes because n and t and stuff like this, they're orthogonal. So and this one is then each one once. So you see that also the length of the cross product has to be 1. So that's like really justifies, this remark justifies why we call it frame. Like frame is usually something that is like reserved, the name frame is reserved to something that is orthogonal to each other and has unit length. If you're a physicist, you probably have seen this notion that it's like an orthonormal basis. If not, then it's also not important. It's just like this definition that they are orthogonal to each other and have unit length. So the important part is here that we have like this kind of frame which depends on the time. So it changes as the curve goes on or like moves, the frame goes with it. And one natural question would be, how is now this frame behaving? Like what is the derivative of that frame, say, for example? Like how does this frame changes as time goes on? And how is that related to some properties of the curve? And that's the next question I would like to answer. The important observation here is that certain properties are encoded in this error frame, and we have seen that already, as like the curvature is related to essentially to like the first like the t and the n. So in particular, we can just calculate the time derivatives of all of the data that we have. So we first take the derivative with respect to time of the tangent vector field, because that's the simplest. T in itself was just the first derivative of the curve. So we take now the second derivative. And now we use the fact that this one is almost the normal vector. So we can rephrase that in terms of the normal vector, but normalized with the curvature. So that's essentially just the definition of the curvature. So the idea here is that we do that now for the other two data also, that we take the time derivative of the curve of the frame and relate that back to the frame itself. Like in this case, it's relatively simple, namely that the time derivative of the tangent vector field is the same thing as the scaled normal vector field. Okay. So that's the first one. Maybe now we start with the second one, which would be B prime, like the time derivative. And we can say, like, because it's a frame, we can write this as some change some constants. We can write this always as this because it's a frame. So every vector can be written as some linear combination of these three vectors because they form like an orthonormal system as we described over there. So some constants, but we don't know these constants and have to determine them. So one of the, like there are two ways. Either we calculate things or you use your geometric intuition. The first part is that because B is a unit vector, and that's true for all times. Like if you change something on a unit vector, then the change of the unit vector, if you change like the vector slightly, will be something that is orthogonal. The change of that vector will be something that is orthogonal to the vector itself. So if B is here and B prime is here, then B has to be orthogonal to B prime. You can also see that again as just like a calculation. So if you take the time derivative of that fact, what you get is that 2 times of B, the scalar product with B prime, has to be 0. Like that. So in particular, you see again that B has to be orthogonal to B prime. So that means that this expansion that we had is that this constant C has to be 0. Otherwise, there's some part in there which is parallel. So that follows that C equals to 0. Then there's a second direction that we would like to look at, namely what happens in the tangent direction. And there we use the fact that like essentially B is defined as like by the third hand rule. So like it's always orthogonal. Like if that one is like in tangent direction, then B is always orthogonal to that. So that follows that like there's no possibility that like this B can change into like something in T direction. And again, like that's the geometric intuition, and you can like say like write this down that if you have B and T equals to 0, what you can say from this one is that you take the time derivative of this, so it's by the chain rule, you get like a formula where you take the time derivative of each of these elements. This one is something we would like to calculate. This one is the constant A. Because in our product, T has N, which is like orthogonal, so that kills it, and T itself has like a unit length, so it's really like just a constant A. And this one is something we calculated already, where T prime was something that is in the n direction. So what we get here is that it's speed times the curvature times the normal. So this one is also then vanishing. This one is vanishing in itself. So what we conclude is that E equals to 0. And again, the geometric intuition is that because B is defined to be orthogonal to T for all times, then they can't change in the T direction. So what we get is that B prime is of the form B times n. And like if you look now at that formula, like the T prime was described by the curvature, and so it made sense to kind of say like that B here is something that is like also intrinsic to the curve, and that is like something that we call torsion. It would be slightly too simple because for some reason people say there needs to be a minus sign, which I can't motivate at all. There is no real reason, it's just convention. For some reason people would like to see that certain things are positive in certain examples. So minus B is usually called tau, and it's called the torsion. So again, there's no real content to the minus sign. So the important part is like the curvature measures how the tangent vector field behaves in relative direction to the n, and the torsion of the curve tells you how this binormal vector field is like behaving in n direction. So just like to give you like a formula. A different way to write this one is then of course that we can calculate this constant in the expression by just taking the inner product. So it's minus B prime in inner product with the normal vector field. So that's how you calculate the torsion. So if I ask you, please calculate the torsion of a curve, what you do is you calculate B, T, and N, take the derivative of B, and then take the inner product of N, and you get a number, and that one is the torsion. And in a very similar way, we can just take the time derivative of the normal vector field. So we make the ansatz again. So this one is, can we expand in terms of some constants that we have to determine, d, t, and e, and f. And then we get like certain formulas by having that n equals to the unit norm. Here we take the derivative again, and that follows then that e equals to 0. So that part vanishes. And then we have the constraint that n has to be orthogonal to t and b. And if you take the derivative of each of these ones, what you end up with is that the d constant is minus the curvature, and here you end up with that f equals the torsion. So very similar calculation as what I have done over there. Is you just take like the derivative of each of these constraints and then analyze that, what it means in terms of these constants. shown so far, and that's like worthwhile to record, is that if C with free series frame given by T N and B, then we have the following equations for the time derivatives, which is T N B equals to kappa of n minus kappa of t plus tau of beta and minus tau of n. And then this tau is, of course, the torsion index. So that's the upshot of our discussion so far, where we just calculated the time derivatives. So you can see, like there's two different viewpoints. One, you say like the B and T and B is like the fundamental one, then you can see this one essentially giving you the definition of kappa and the torsion. So like the curvature and the torsion describe just like the development of this particular frame field along the curve. So that's like one very mathematical viewpoint, is that like that the curvature and the torsion, the twisting and the bending are described completely in terms of this frame that says like like how much you twist and how much you change is encoded in like exactly these two variables. That's maybe as a like last remark, that would be just like a remark for the people that are a bit more interested in the mathematics behind there. We can write these equations a little bit more interestingly in matrix form, where we say where you have to calculate like that a little bit like in a way that like you take like this line here times this line here to get like the time derivative of the first t. So that's like just like a reformulation of exactly this equation here, that the time derivative of t equals to kappa times n. So that's just like a reformulation. We have two observations. The first one is that this one is antisymmetric. And essentially that this one is antisymmetric comes from the like a very simple like way, namely this one is essentially the derivative of the fact that T n and B are like orthogonal and normalized. If you take like the time derivative of that one, what you get is like the antisymmetric version. So it's essentially like that this one is antisymmetric. It's like the same argument that I had before, that if you have a vector and the derivative of that vector is something orthogonal to that, if it's like normalized to be 1. This one is essentially equivalent to these three elements being like normalized and orthogonal for all times. That explains already why this one has to be 0, this one 0, this one is 0, and why they are normalized. The only thing that is not explained is why this one is like 0, from the fact that it's like time dependent. And this one just follows from because we choose a very special n. Namely, there's like a lot of like normal directions to a curve, right? Like if you have like in 2 dimensions, there was like only 1, but in 3 dimensions, if that's the curve, then the normal direction would be everything here. Right? Like, there's nothing like particular, like why should I like choose one of these special norms? And like the important point here is that we particularly choose like one n that is normal to the curve, right? Like if that's the, because you also like that's the tangent vector, then the normal direction is something that is normal, like something in that plane. But the curve singles out one particular normal vector, namely the one that is given by the second time derivative. So that's a very special normal derivative. And that's why sometimes this n is not just called normal vector field, but like principal normal. Like principal and things, like something special that is derived from the curve. And because we choose that, we get a 0 here. So in some way, like like these equations, the differential equations, they encode like these 2 assumptions. One of them is just like that you have like a frame and all of them are orthogonal and normalized all the time. And the other one is that like n is like rather special to the curve. That's why you get the 0 n. So that's like in some way like all the assumptions that are encoded in these kind of equations over there. Yes, and I think that's enough for today. Yeah, it's like homework exercises. I give you mostly some calculation. That's maybe also something that you, like in a lecture, I will mostly discuss like some bit more theoretical elements, but you're not really like required, for example, for the exam to know like the proof that I showed at the beginning. That's mostly something that I show you because I find it interesting and I think you should know that. But most of these a bit more advanced proof is something that is not relevant for the exam. Like you should know the content of the theorem, but not so much the proofs of them. But like you should definitely be able to calculate certain things. So the homework will be in order to give you a certain curve, and you have to calculate like the curvature and the torsion of that curve. Just like to give you some idea of expectations. And then see you next week.
Most of us are minor in mathematics.
Okay.
So I think maybe more proofs can be taught on the class.
Okay, like the problem was like I give that lecture like last time already, and then the problem was that too many people were not able to follow like the proofs too much.
But most of us are minor in mathematics, so I think it can be harder than this part.
Okay, so you're saying it's too easy at the moment?
Yes.
Okay.
I want more proofs be taught on the class. Not that I don't expect all the details. Maybe some without detail and some intuition can be give us. Yes.
Okay, good. Thanks for telling me. It's good. I will take that in mind. Yeah, sorry. The dot over there, like this one is wrong. The dot over there is wrong. It's just, well, it just should be just the norm of P, and then you take the wages of that.
And I have another question is this problem, like why does the series of P and Q, they must converge to a point? I don't think it's too obvious to see.
No, it's not like too obvious. The point is that what you should like prove is that like if you choose like a different P, then the Q is always like on the arc between this Q and this Q. Like what's not happening is that this Q, which I kind of like intuitively draw on that line, is like happening to be on that side.
So it's impossible that one is on the right and one is on the left.
Yes.
They are on the same side, so they can converge.
Yes. So it's not possible that like the point is on the other side, because if you try to draw that, what happens is that like these two circles, the blue ones at P and the ones at P prime, they intersect at 3 different points at least.
Yes.
And if you have 2 circles which are intersecting at 3 different points, then they have to coincide. So that's like an argument which I didn't.
So this is more like a draft that we should fill in more details.
Yeah, so I will post like in Canvas if you're more interested in that, like how to read it.
Thank you.
This is the composition of our class, and this is the translation.
Okay.
Most of us are minor in mathematics and applied mathematics.
Okay.
So I think the class can be higher.
Okay, good. Then I check if that like how it was last time, but that's really good feedback. Yeah, thanks. Yes.
Do you have a class on Sunday, right? Or we do not?
We do. It's a good point, yes. Yes, because it was shifted, right? Like it was now shifted.
Yes.
Is that to this Sunday or like?
I think due to the arrangement, they say it's on this Sunday.
Okay, good. Yes, that's good point. See.